All right, welcome everybody. Today we're going to talk about Calc Lesson number 32. Given the fact that most of you are watching this your first day back from break, we thought it would be a good idea to review everything that we had been doing in Chapter 3 so far, and then we're going to have a brief introduction to the concepts called concavity and points of inflection. So, as a reminder, where we left off, one of the most important things we were talking about was how to find intervals of increasing and decreasing. And again, as a reminder, we were doing that on open intervals. We did do certain things on closed intervals, which I'll remind you of in a minute. But for the most part, when we were talking about increasing and decreasing, we were doing it on an open interval. So if you wanted to find those intervals, you would follow the three-step process listed here. And again, you have all this in your notes already, so I didn't copy it again for today's notes. So simply refer back to those worksheets as needed. Step one, you would go ahead and locate the critical numbers of f on the interval and then use them to determine test intervals. A reminder that in order to be a critical number, that includes not only values that make the function zero, but it also includes things like asymptotes, cusps, and vertical tangents, which we've seen a few of so far, and we're going to see much more of to come. Then step two, you would go ahead and determine the sign of the derivative at one test value in each of the intervals. Based on the signage, you would then determine whether the function was increasing, decreasing, or constant. Pretty much only increasing and decreasing. We never really saw any that were constant. And then as a reminder, these are the three possible things that can happen if when you are testing in the first derivative, turns out that you're greater than zero, then that is where the original function is going to be increasing. If you test the first derivative and you get something that's negative or less than zero, that's where the original function is going to be decreasing. And if it turns out that your derivative is exactly equal to zero, then that's where you would say that you are constant on that open interval. So again, that's the three-step process for how you would define the open intervals of increasing and decreasing. Then we talked about the first derivative test. So we kind of formalized that process. Not only does that allow you to test for where things are increasing and decreasing, but it also then allows you to determine whether or not there is a relative maximum or minimum. So if you do your first derivative, again, that's why it's called the first derivative test. And if when you test, you change from increasing to decreasing, you can then conclude that at that value C, you have to have a relative maximum. If you have a sign change from a decreasing to an increasing, then you can conclude that at that C value, you have a relative minimum. And then, of course, if there is no sign change, it is neither a relative max or a relative minimum. To remind you why it's a relative max or minimum, remember, because of the fact that this is an open interval, it means that the graph goes on forever. So there could be numbers that are larger, there could be numbers that are smaller. You are simply finding a relative max or min, meaning the highest or lowest value in the area. Another important thing to remember about the first derivative test is that whilst you are testing in the first derivative, the information that you conclude is actually about the original f. So again, we went over a whole bunch of those prior to break. You actually will see these concepts reviewed again in the upcoming days. So we're kind of just giving you a brief review here in lesson 32. So again, because we're going to see so many of these, let's just do a very easy one just to make sure we remember the mechanics. And then let's go ahead and we'll move on after that. So let's say you're given the function 6x minus x squared. You're going to go ahead and find any critical values or any critical numbers. Find any open intervals where the graph is, where f is increasing or decreasing, and then use the first derivative test to identify any relative extrema. So hopefully you remember that the first order of business is to go ahead and take the derivative. Again, I kept this nice and simple. So the derivative of 6x minus x squared is 6 minus 2x. You're going to go ahead and then try to find the critical value. So I'm going to set this equal to 0. Then I notice that I can go ahead and factor out a 2. That's going to leave me with a 3 minus x. And remember, when it comes to evaluating with the first and come to think of it, the second derivative, which we're going to talk about the next few lessons, you should really only factor things out. You shouldn't divide things away, because if you divide away negatives, it changes the signs. You should really just factor things out. Based on this factorization, your critical values are only things that make the entire expression 0, which in this case would be 3 and 3 only. So 3 is my only critical value or my only critical number, which means I'm going to now set up a number line and I'm going to go ahead and put 3 as my tick mark. I then have to choose something that's larger than 3 to the right and something that's smaller than 3 to the left. I personally prefer to test in factored form as opposed to standard form, but it's up to you. And again, I like to sometimes say bigger is better. It just makes it a little bit easier to figure out if it's positive or negative. So I'm going to test in the first derivative, of course. I'm going to choose 10. If I choose 10, I'm going to get 2 times 3 minus 10. All I care about is that that's a negative number. Positive 2 times a negative number gives me a negative here on the right-hand side. Remember, when you're doing the testing, we don't actually even care about what the y value is. All we care about is it positive or negative? Something that's less than 3, I'm luckily enough, I'm going to go ahead and choose 0. If I choose 0, I'm going to get 2 times 3, which is clearly a positive 6. So I'm going to go ahead and declare that a positive. And again, sometimes I finish it all the way through and find the value. Sometimes I don't. Some of you at this point might not even really need to show the testing. You're kind of doing it in your head. Remember, that's a perfectly fine strategy for homework problems or practice problems, perhaps on a test or quiz. You'll just want to show all the work to be safe. So from here, what can we conclude about f? Remember, even though you're using the first derivative to test, your conclusions are about f. So we can say that the function f is increasing from negative infinity to 3. We can say that the function f is decreasing from 3 to infinity. Remember, you're only going to use parentheses for increasing and decreasing, always. Then notice here that because at 3, the graph changed from an increasing to a decreasing, the only way that that could happen is if there was a relative maximum at some point at 3. So we can just say that f, again, has a relative max at 3 comma something. And hopefully you remember that to find the something, you have to go back to the original f. So I'm going to find the value of the original f at 3. 3 times 6 is 18 minus 3 squared is 9. So it turns out that f has a relative maximum at the point 3 comma 9. So again, that's a very simple example for everything we had done prior to break, but hopefully that's enough just to kind of refresh yourself. You've done many more examples that are much harder than this back in your notes and homework. So if you need to review more, just simply go back and take a look at those. Then finally, the last thing we talked about, this is just a graph that kind of takes what you were finding on the previous screen and just giving you a visual. Remember, you're not just finding these values and kind of forgetting about them. The ultimate goal is to create the graph that it connects to. So this is obviously a quartic polynomial, which is much more complicated than the quadratic on the previous screen, but it's just reminding you that those local maxes and minimums, those are where the graph is changing from increasing to decreasing and vice versa. So again, just kind of a visual to set the scene for you. Then, Then, as another reminder, the other thing we talked about was how would you find absolute extrema on a closed interval? So a closed interval, remember, it's not going to be a secret whether the interval is open or closed. We will tell you. And if you are on a closed interval, it means that you are finding the absolute max or min because you know that you only are looking at a set x to start and a set x to end. So process is a little bit different. Step 1, you're still going to find those critical values. Then step 2, you are going to evaluate in f this time at each of those critical values. Then you're going to evaluate at f at each of the endpoints. And then you're going to conclude that the highest value is the maximum and the lowest value is the minimum. So again, the biggest difference here is that you are simply taking those values of x that you find and plugging them right back into the original f and then just looking for the largest and the smallest one. Most of those examples we had done, we had kind of used a table format. So here's one that's already done. And again, you should have several in your notes as well. So let's say you wanted to find the extrema on the closed interval, -1 to 3. And again, you'll know it's a closed interval, 1, because there's no infinities, and 2, because of the brackets. So your function in this case is 2x minus 3 times x to the 2/3. So you would, of course, take the derivative. It would be a little bit more complicated because as you do x to the 2/3, you would have to take x to the 1 less power, which would be -1/3. You would then move that to the denominator to become positive. Then you would find a common denominator and factor out the 2. Again, that's all the algebra that we've already gone over before break. Based on that, which is the easiest way for you to determine critical values, you would find the value that makes the denominator 0, which would be 0. You would find any values that make the numerator 0, which would be 1. And then because of the fact that you are on a closed interval, you also want to consider the endpoints. So notice here at my table, -1 is my left endpoint, so I'm going to put that first. 0 is my first critical number. 1 is my second critical number, and then 3 is my right endpoint. So you're always going to list those x's from the smallest to the largest. You're then going to plug them all the way back into the original f using a calculator as needed, and you're going to go ahead and find the corresponding y values. Decimals, positives, negatives, anything is fine. Once you find your possible y values, you're going to locate the largest one, which in this case would be 0, and you're going to go ahead and conclude that that is the absolute maximum. Then you're going to locate the smallest one, which in this case is -5, and you're going to conclude that that is the absolute minimum. And again, that would be the point 0, 0, and this would be the point -1, -5. So this example looks a little different than the ones you did prior to break, just in terms of the setup. But again, any format is fine as long as you come to the correct conclusion. So hopefully that reminds you of everything that we did before break. And now we're going to go ahead and move on to something called concavity. So maybe you've heard the word before, maybe you haven't. Maybe you've heard it just kind of in general, not necessarily related to math. But concavity is the direction in which the graph bends. A graph is said to be concave up at a certain point if the tangent line to the graph at that point is below the graph. And a graph is said to be concave down if any of the tangent lines are above the graph. So here's an example of a function. So first you see the concave down part. So concave down is in blue, and notice that any of the tangent lines that could be drawn would always be above. Then notice in red, that's your concave up location. And notice that any of the tangent lines that you were to draw would be below. Concavity has a lot of applications, and you eventually are going to have to draw things that are concave up and concave down. So if you have any hope of doing that accurately, you first just have to be able to recognize where a graph that's already drawn is concave up or down. So I have for you a ton of examples. There are lots of different ways for you to kind of define and think about concavity in your mind. So here's a bunch. So notice in the first two examples, you have, a familiar shape, which is a quadratic. And notice that in both of these examples, it's concave up or concave down the entire time. So if you're using the idea of tangent lines to think about concavity, notice that where it's concave up, all the tangent lines are underneath, where it's concave down, all the tangent lines are above. For me, personally, the easiest way that I try to think about concavity is concave up means where the graph would hold water, and concave down means where the graph would dump water. So imagine you have your concave up graph. If I tried to fill this parabola with water, the water would stay in nice and exactly, and I could go ahead and fill up that parabola. Whereas if I were trying to fill up this parabola here on the right, obviously the water would be spilling out, which means that that part of the graph would be concave down. Notice here in the second set, in the top right, you have just part of a graph. So yes, the graph on the left is concave up, again, because of the fact that you're either holding the water or because the tangent lines are underneath. Yes, you might think to yourself, well, wouldn't the water dribble out here on the left? You don't know what's actually happening to the left, and it's fine if it doesn't actually turn back up, as long as the curve that you're looking at would hold the water at that point or have the tangent lines underneath. Perfectly fine to be concave up. And then over here on the right, concave down, water is spilling out, and tangent lines are above. Then here in the bottom left, I want to show you that you can be concave up and decreasing. That's what's happening in the top left. Or you can be concave up and increasing. Same thing for concave down. You can be concave down and decreasing, or you can be concave down and increasing. So don't think that, decreasing has to go with one or the other. They can have all the possible combinations. And then finally over here on the bottom right, again, using those tangent lines, not only does concave up mean the tangent lines are all underneath, but it actually means the slope of those tangent lines is increasing. Whereas if you're talking about something that's concave down, again, not only are the tangent lines above, but the slope is decreasing. So we thought it would be helpful to just kind of show you as many possible definitions of concavity as we possibly could. And again, you're going to choose the one that makes the most sense for you. In the previous examples, the pieces of the graph that I showed you were only concave up or concave down. For our purposes, we're going to be looking at graphs that potentially change from concave up to concave down or vice versa. Also, you can use abbreviations. So most of the time for concave up, we would say CU. And then for concave down, we would say CD. So taking a look here, the water is being filled, concave up, concave up. Then we get to a particular location where now the water is dumping out. So there's my concave down. Then we get to another location where the water starts filling again and becomes concave up. Those, dotted lines, those points there, they have a name, which we're going to talk about in a second. But again, the majority of graphs that you're going to see are going to have some change in concavity. That was just a mystery graph that I made up. Here's kind of one that's a little bit more familiar. This is a polynomial. It's a quintic polynomial because of the fact that there are 5x intercept. Notice that all the concave downs are in blue and all the concave ups are in red. Now, in the lessons that follow this week, you are going to find an algebraic process to actually find where the graph is changing from concave up to concave down or vice versa. But for today, all we're asking you to do is eyeball it. So if we were to give you a graph like this and say, where is it changing concavity? Notice that in the red, that is where we would say that it's concave up. And then we're saying that at this location right here is where it changes to being concave down. This location here is where it changes to be concave up again. And then this location here is where it turns to be concave down. Those are called points of inflection, which again, we're going to define in a minute. And for now, again, you're just estimating. So what if you estimated a little bit higher or a little bit lower than the points that are shown here? That would be perfectly acceptable as long as you're close. Again, we're going to find out the exact process in the upcoming lessons, but for now, you're just trying to give a reasonable estimate. So again, the point where there's a change in concavity, that is called a point of inflection or an inflection point. And these are the three most common kinds. So notice in the left here, so the graph is concave down, it's a nice curve. Then there is clear point where the graph now changes to being concave up. Notice that the one in the middle, you have a graph that is concave up, and then there's a point that kind of looks flat horizontally where it changes to be concave down. And then in the third example, you have a point where it kind of looks vertically, like it's changing from concave up to concave down. So again, as long as there is any change in concavity, it is a point of inflection or an inflection point. And then again, these are just kind of the three most common types. So to get us started here, and again, this is on your worksheet so you can fill it in, describe the intervals where the graph is concave up or down, and then locate any points of inflection. So because I'm trying to kind of just get you acclimated to what these mean, notice that the graph is kind of already labeled for you. So you really just have to make, the connection in your mind of what's happening. So again, concave up, I'm going to call that CU, and that is where the water would be held. So I can see that that is this location here. When you're telling me the intervals of concavity, just like increasing and decreasing, you're telling me from what x to what x, and you're only going to use parentheses. So because it goes all the way to the left, that would be x equals negative infinity. All the way up to x equals 1, I can say that the graph is concave up. Then the graph is going to be concave down, starting at x equals 1, and then all the way to x equals positive infinity. A point of inflection, which I call a POI for short, is where the change happens. And here it looks like it's the point 1, 2. So again, to get you started, all you're going to be asked to do is look at a graph that's already made and determine concavity and possible points of inflection. Here, the point of inflection is pretty obvious, but if you have to estimate, that will be fine. Let's take a look at another one here, which again is already labeled for you just to kind of get it straight in your mind. So starting with where is the graph concave up? The graph is concave up from x equals negative infinity to x equals 0. The graph is concave down from x equals 0 to x equals positive infinity. Again, you're going to assume that the graph goes on forever. The point of inflection or the inflection point would be the point 0, 0. These are those nice, smooth polynomial curves, which obviously makes it pretty easy to identify. Can get a little bit harder for something like this. This is a rational function. Remember, that means that it has those asymptotes. So here, if I ask you to determine concave up and concave down, you kind of have to think about it a little more. I see this piece on the left and I say to myself, okay, that's going to hold some water. And I see this piece to the right and I say to myself, okay, that's going to hold some water. Again, notice that any tangent lines that you would draw would be underneath. So that is where my graph is concave up, which is in more than one location. The piece all the way to the left, that would be from negative infinity to the asymptote, which is -5. Then again, from the right asymptote, which would be 5 to infinity, it's going to be concave down in the middle. All the water would be spilling out and all the tangent lines would be above. So I would say that that's concave down from x equals -5 to x equals +5. And remember, those are x values and you're only going to use parentheses. Careful here about a point of inflection. By definition, a point of inflection has to be a point. It cannot be an asymptote. So we are going to say that there are no points of inflection. Yes, there is a change, but because it happens at a break in the graph or a vertical asymptote, it cannot be a point of inflection unless it actually is a point. Hopefully you remember this guy here. This is, of course, the square root of x. Perhaps you never thought about a graph like this before in terms of, concavity, but if you were to draw the tangent lines, all the tangent lines would be above, all the water would be spilling out. So it's safe to say that this graph is concave down the entire time because of the fact that you can only take the square root of positive numbers. The graph only starts at 0 and then goes all the way to the right. So this graph is concave down from 0 to infinity. And again, there are no points of inflection because there's no change in concavity anywhere on the graph. Finally, I always think it's kind of a good idea, now that you're learning all this calc stuff, go back to old stuff and kind of look at it with your calc glasses on. These are exponential growth and decay on the left and growth on the right. I now want you to think about it in terms of concavity and any points of inflection. So over here on the left, 1/2 to the x, again, think about where your tangent lines would be. Your tangent lines would all be underneath. It would be holding all the water. So it would be safe to say that this graph is concave up the whole time, which would be from x equals -infinity to x equals +infinity. Because there's no change in concavity, there's no point of inflection. And then over here on the right, all the tangent lines would still be below. All the water would still be held. So this is another example of a graph that's concave up the whole time. And again, there's no point of inflection. And again, notice that the graph on the left is entirely decreasing, where the graph on the right is entirely increasing. But that's perfectly fine that they're both concave up. So I kind of wanted to just show you a mix here. And then finally, I thought it would be kind of interesting just to kind of think about some applications, inflection points. Maybe you've heard the word before, or maybe if you haven't, again, I always think it's kind of nice to go back to old stuff with your calc glasses on and kind of look at it. For those of you who are in AP Stat, that should look familiar to you. That is, of course, the normal curve. Whether you've heard Mr. Plush use these words before or not, exactly one standard deviation away from the mean, those are supposed to be inflection points. Here underneath, these are the parts of the graph that are supposed to be concave up. Then it is supposed to change to concave down, and then it's supposed to be concave up again. So if you've been drawing those normal curves, you should keep an eye on your concavity. The reason why the concavity changes has to do with rates of change, which we're going to talk more about next time, but feel free to ask Mr. Plush to talk more about it in the meantime. Another application of an inflection point has to do with things that are cool, things that start off as being a fad and it's too early to tell, is people going to like it? Are people going to use it? Examples, think about things like TikTok, think about things like the iPhone, think about fidget spinners or the Android phone, things that, kind of come out and some people get on board and they think that it seems cool and they're not sure whether or not it's actually going to take off. Well, based on some point of inflection here, that's where we either decide that, nah, it's the wrong horse, no one's going to like that, they're going to disappear. I mean, think about the last time you saw anybody with a fidget spinner. Or it's going to become the next big thing and the growth is just going to explode. And then eventually everybody has one. It becomes mainstream and lame. It's too late to get on board, too late to make money, and people kind of jump to the next big thing. Another application, maybe if you've heard it in economics or in any of your business classes, but just business in general, there comes a time in a business where there is an inflection point where the business is either going to take off and it's going to grow or it's going to decline. I mean, think about Shark Tank. If you ever watch the show, and if you don't, you should. Businesses, things go viral or they get a really big bump from being on the show. And sometimes they're able to keep up with demand and people love it and the business grows and explodes and Mark Cuban makes $1 billion, maybe not a billion, or people decide now we don't need that, or too many people knock it off and there's too much competition and then the business kind of dies. And then to finish it off, you're going to hear COVID-19 referred to as an inflection point, not only in terms of business, but honestly, in terms of life. If you just kind of think about it, we were all kind of cruising along business as usual last January and February. All of a sudden, COVID-19 hit, and that is what we would call an inflection point. Most people think of it in terms of the digital disruption because people were not going out, people were not going to stores, people were not going to restaurants. And then because of that disruption, some people were able to meet the technology and survive, and sometimes not only just survive but thrive. And then sometimes people were not able to and they kind of missed the boat. I mean, think about your favorite restaurants or your favorite stores. Think about whether or not they ran specials or they came up with an online food system, an online delivery system, or an online order system. Those are the guys who are still around. And then think about the companies that didn't have a way to kind of reach you on the internet, and maybe those aren't going to be around for so long. So I always think it's kind of cool to see where the calculus, meets the real world. So hopefully you agree. You're going to go ahead and try homework number 32. It's a worksheet in class notebook. It actually looks a little different than what we've been doing today, just in terms of the way the questions are asked, but I'm confident that you'll be able to handle it. And we'll be talking much more about concavity and inflection points in the coming days. So thanks very much for tuning in, guys, and we will catch you next time.